Let's talk about the special kinds of circuits, Euler and Hamilton circuits in a graph. And Euler circuits actually arise from a problem that Leonhard Euler investigated regarding the Prego River and bridges over the Prego River in the town of what was then called Königsberg. In 1736, he actually came up with a result regarding that, and we'll talk about that in a few minutes. But first of all, let's talk about what an Euler circuit has come to mean. Suppose we have a graph. An Euler circuit in a graph is a circuit, which means that it's a closed walk that does not repeat edges, that contains every edge of the graph. So the consequence of that is that it does not repeat edges, but it must contain every edge. So each edge crossed exactly once, and it returns to the start in so doing. So it ends where it starts, and it crosses each edge exactly once. So an Euler trail is a little bit more general term. An Euler trail in a graph is a trail that contains every edge of the graph, but it does not have to be a circuit. In other words, it doesn't have to be closed. But an Euler circuit is an Euler trail. It's just more required of it that it be closed as well. So it is a special type of Euler trail. So an Euler trail also uses each edge exactly once, but it needn't return to the start. So just real quickly, here's a couple of graphs. This one, G1, we could traverse every edge in this by doing something like the following. Let me start at B. We could start anywhere because it's going to be a circuit, but I'll start at B and do those first of all. And then once I'm back to B, I'll just cross each of these here. Notice that I did go through vertices more than once, but that's okay. The requirement is that we not cross an edge more than once, and that we cross each edge. So nothing to do with how many times we cross a vertex, and I'm numbering these in the order in which I actually cross them, like so. So I did cross each edge exactly once, and it was a circuit. So this is an Euler circuit. The walk I've sketched there, and I could write that down as a vertex sequence the way I did it. I did B, C, D, E, F, G, H, A, B, and then I did D, followed by F, H, and back to B. So that's a way to describe that, since it's a simple graph the way I have it there. This also applies to more general pseudographs, but the one I have sketched here is a simple graph, so a vertex listing there gives you complete information about it. So in this other one here, I can do an Euler trail. You might ponder whether you can do an Euler circuit. We have that 3 extra edges here in the middle from C to G. I didn't name the vertices in the middle there. I suppose I should have. That's H, so this might be I, and this might be J then, like so. So yeah, can we draw a trail here at least that works? And one way we could draw a trail would be to start at C, go all the way around, so we'll get the outside taken care of, and then go in, and then from there go all the way around on the inside back to I, and then we have this last part here and shoot through and get G. So if I were to number those, the way I did it, I started with C. 1, 2, 3, 4, 5, 6, 7, 8 in order like so. And then I went in, that was 9 right there. Then I did 10, 11, 12, 13, 14, 15, and then 16. And this edge right here was 17, like so. So you could do the same thing and write a vertex sequence. Let's see if I can do that. C, D, E, F, G, H, I, A, B, C, I, D, F, J, H, B, I, and then shooting down to J and then to G. So it's kind of long, but there it is right there. So that gives us an Euler trail. Right, so we can actually characterize exactly which graphs have an Euler trail. First of all, they have to be connected. There's no doubt about that. And so if we think about when a graph has an Euler trail, let me just do a little preliminary. Let's suppose if G has an Euler, actually I want to go for circuit first of all. If G has an Euler circuit, say we write it as V0 and V goes to V1, then to V2. And so I'm going to draw this kind of in a circular pattern, but it doesn't actually have to be a circle. I'm just saying which vertices we visit next. So V3, then V4, then V5. Let's see. Let me do something here instead. Let's go from V3 to V1. To V1. So we're going to go back to V1, and then we'll go to V4, V5, Z6, V4, V5, V6, and then let's go to V1 again, V3, and back to V0. So this is just the order in which we visit all the vertices, all right? That's not actually the way the graph will look, and I'll actually give a sketch of a graph here. But this would be intending to be an Euler circuit, so every edge is represented. So that would mean that there's an edge here from V0 to V1, and one from V1 to V2, and one from V2 to V3, then back to V1, right? So we're going back to V1, etc. So the important ingredient here that I want to emphasize is that for each of these edges that I have here, actually for each vertex, I should say that each time a vertex appears here, so for example V1 appears here, then I've used an edge on either side of the appearance of V1. So I've used two edges, and over here again V1 is visited, I use two more edges, and then over here V1 is visited, I use two more edges. So because I have to use every edge, each edge is crossed exactly once, the degree of V1 had to be 6 in this particular case here, right? And the degree of V3 would have to be 4, because I use 4 edges for V3, one here, one here. Maybe I should use the green for that one there, just to illustrate that. So for V3 I use 2 edges, one on either side there, and one on either side here. And that's one of the reasons why I drew this as a circular pattern. So any one of these could serve as a start, but the start and the end for V0, for example, would also have an edge on either side, and there's 2 edges there. So the degree of V0 must be 2, and the degree of V3 must be 4. So each of them is even. The graph here, by the way, if you wanted to see a depiction of the graph, would look something like the following. So let's just draw the vertices any sort of order. I'll put V0 right here. That'll be kind of in the middle. And then V0 goes to V1. I'm going to put a V1 up here. I'm just putting them kind of arbitrarily because it doesn't really matter how you draw it. It's the connections that matter, if you remember, as we've said this before. So let's go V2 over here, and V3 over here, and then V3 goes back to V1. Whoops, that looks kind of sloppy. Right, so V3 goes back to V1. That's what's going on here. And then V1 goes to V4. Why don't we put V4 over here? And then V4 goes to V5. V5 goes to V6. V6 goes to V1. And then V1 goes to V3. Oh, so look, there's a double edge right there, and that's fine. There's no problem with that. But the key ingredient here is that however this works out in any such circuit, a Euler circuit, the degree of each vertex has to be even. In fact, that's all we need as long as the graph is connected. If G is a connected graph of order n, more than 2, then G has an Euler circuit if and only if every vertex is even. So the one direction we've kind of indicated, and I'll write then in the proof here, given an Euler circuit, say V0, V1 out to some Vn with Vn equal to V0, then each appearance of a vertex uses two edges incident on the vertex. So a total of so a multiple of two edges are incident on the vertex according to the number of visits to that vertex. The number of visits times 2, and because we can start or end at any place, that also corresponds to the starting and ending vertex, which in one way of looking at it has one edge ending there, one edge ending there, and one edge starting there, and that's also two edges used at that appearance of it as a start and the end, just as the V0 in the previous example. So every vertex is even if it has a Euler circuit, hence every vertex is even. On the other hand, conversely, if G is connected with n greater than or equal to 2 vertices, and each vertex is even, then pick one, say V0, just to name it, and from there, since it's got an even degree and it's connected, the degree of V0 is greater than or equal to 2, right? Because it's connected and there's at least one other vertex there. It has to have at least one edge, but it's even, so it has at least 2. And from there, find the walk, I guess we call it trail, let's call it, find the trail that is no repeated edge, no repeated edges, of maximal length, and I'll write it out as V0, V1, V2, all the way out, and then we have some duplicates along the way here if it goes back and visits a vertex again, and we'll come out with Vn, like so. So this is the trail of maximal length with no repeat. So, you know, if I depict this as a V0, it goes to a V1 here, it goes to a V2. It might go back to a V1 like so, and then go on to a different vertex, a V3, etc., and on down to, and then it hits something they'll call Vn minus 1, and then it hits Vn. Okay, and that's where it ends. Okay, has to end because there's only finitely many edges. So we'll find the one of maximal length, and there will be one of greatest length if we take all these different finitely many possible trails. So my claim is that Vn equals V0. That's the claim. Vn equals V0. We had to end where we started, because if not, let's look back. If not, then as we're thinking about going from Vn minus 1 to V0, we're going to go down here like so, to Vn I mean, because Vn is not V0, each time Vn appears, and a pair of edges is used, but the degree of Vn is even, so Vn minus 1 to Vn uses only one edge. Well, that can't be. There must be one more, unless Vn equals V0. So this must be the case. Because if there is one more, then we can still go on further. If there were another edge there, we could continue on, but there must not be, so it must be Z0. This must be the case, like so. So that's almost there. Now the claim is that this is an Euler circuit. This is an Euler circuit. If not, an edge remains, because it is a trail, so it doesn't repeat the edges. So an edge remains, and all vertices incident on an edge have an even number incident on the vertex. Why is that? Because every time in that circuit we've used an even number of edges each time we pass through a vertex. And so now we know that Vn is V1. There's our last edge there, like so. Then we've used an even number of edges at each vertex. So if we have another edge, let me draw one up here, that remains, then there's an even number of edges incident on each of the vertices that still have an edge. By connectedness, there must be an edge incident on the original circuit that is not consumed in that circuit, that is not used in that circuit. And so the same process can be proceeded. Say an edge is incident, let me not put it that way, an edge will be incident on a vertex in the circuit, and the same process produces a side circuit at that vertex. I'm going to run into this next bit here, so what I'll do is draw the picture of what's going on here now. So if an edge remains, maybe I'll just go back up and do it here. So what happens if there is an edge like this, then if we start here, we will have an odd number of vertices left after we use this first green one here. And if we proceed in the same way, we hit a vertex here, well, its degree is even, because we've left an even number of edges there after using an even number of edges, and we can always proceed out of that, and we can create another trail that has to end back up at that vertex there, the one that I've called V2 here. So our original circuit could be extended by, rather than going back to V1 here, as we did, go along this side circuit and then go back to V1 and continue on. And that way we get a larger circuit. So by patching this in, patching this circuit in creates a longer trail, a contradiction. Since we picked the maximal one, so the original circuit must use every edge, and that would make it an Euler circuit. So it is an if and only if. It is a an equivalent statement. It gives us a complete characterization, and I will give you some examples, some more examples, and talk more about this in the next clip.